Okay, the first step in conducting our hypothesis test is making sure we carefully craft what are called the hypothesis statements. And there are two statements that go together that capture the essence of the claim that we want to test. And the two statements, they're called the alternate statement and the null statement, have to be mutually exclusive and collectively exhaustive. The alternate or alternative hypothesis statement contains the embodiment of the claim that we want to prove, the idea that we're trying to test for. And that usually states that some population parameter is in some way different from or some distance away from some null value, some either historical value or benchmark value. And the null hypothesis, on the other hand, says that no, there seems to be no statistical evidence that would make us think that this population parameter is distinct from the null value. For the alternate statement, we only accept those results if the statistical evidence from our sample is really strong or really significant. And what we formally do when we do our test is actually we make a decision about the null hypothesis. We really, if the evidence is strong enough, we would reject the null hypothesis that things are not distinct from the benchmark value or the null value. If the data is not significantly different, then we would say no, this could just be random fluctuation around this old value, and we're not seeing strong enough evidence to say that something different is going on. So technically, we use our statistical data to either reject the null hypothesis or not reject the null hypothesis. Of course, if we rejected the null hypothesis, then all we're left with is the idea that the alternate hypothesis is going to be taken to be true, at least to whatever level of significance we choose. When we create these labels and symbols, we use the label H sub A for the alternate hypothesis and H sub 0 for the null hypothesis. And I've put in blue highlight below the table on this slide an example in symbols where we've got some null value of the mean that I'm calling mu sub 0. And the claim being made here and being tested for is that the population parameter is somehow different from this null value. Maybe it's greater, maybe it's less, but we're claiming that things are not at this null value. So we would embody this, we'd capture this in this hypothesis statement in symbols. H sub A, our alternate hypothesis, says that the population mean is not equal to whatever the value of mu sub 0 is, that null value. And this is going to take on some real value. It could be 26 days or $3,700 or whatever is some benchmark value or some reference value that, in this case, we're claiming that our population mean is not equal to that null value. And going along with this alternate hypothesis statement would be the complementary null hypothesis statement that says that our population mean is equal to mu sub 0, whatever that value is. And what we're saying here is not that the population mean is exactly equal to mu sub 0, but that the statistical evidence is not strong enough to suggest that the population mean is really something very different from mu sub 0. Okay? And one or the other of these statements must be true. The two are mutually exclusive and collectively exhaustive. Let's take a look at some of our previous example statements and see how we would capture those in symbols. So these are the three statements. We want to test that greater than 14% of customers will buy some new product, that our new machine or new equipment will reduce cycle time below 12 minutes, and as a third distinct statement or distinct claim that we want to test, that a typical worker worked something other than, either less than or equal to, so worked not equal to 40 hours last week. And we'll look at each one of these three in turn. So if the first claim is that greater than 14% of customers will buy a new product, the alternate hypothesis statement should capture that claim. So the alternate statement, and again, this is a proportion of customers that are going to be buying this new product. So the population parameter in this case is a proportion, population proportion, designated with an uppercase P here. And the claim itself, as captured by the alternate hypothesis statement, is that population proportion is greater than 14% with some new product. And perhaps, as we'll see, what we'll go out and do is some test marketing of this product, and we'll on a sample of customers, and we'd investigate whether or not the data supports the claim. The null hypothesis statement that would go along with this hypothesis test is that population proportion is less than or equal to 14%. So if the evidence does not very strongly or convincingly tell us that the population proportion is greater than 14%, then it must be either less than or equal to 14%. So those two statements are complementary. They are mutually exclusive and collectively exhaustive. Let's look at another one. Some new piece of equipment is going to reduce our cycle time in some process to below 12 minutes. Now, if we're looking at cycle time over some large number of iterations of this process, or a large number of parts being manufactured, if it's a manufacturing process, then what we would look at here is the average cycle time to see whether or not it's below 12 minutes. So the appropriate statements there would be in the alternate statement that our average cycle time is less than 12 minutes. This captures the claim that's represented in words right above, that this new machine will reduce cycle time below 12 minutes, mu less than 12 minutes. The null hypothesis statement in symbols would be that mu is greater than or equal to 12 minutes as the complement of the alternate hypothesis statement. And a third example, if we want to claim that a typical worker worked something other than 40 hours last week, then our alternate hypothesis statement would be that mu, on average, the average of the time worked, population mean, is not equal to 40 hours. And the complement captured in this null hypothesis statement would be that mu is equal to 40 hours. So here we see how we can capture these symbols, these statements in symbol form. All right, the last thing I want to cover in this brief segment is the idea of a one-tailed versus a two-tailed test. And this really depends on, there's a description that captures the idea of on what side of this sampling distribution would our sample have to fall in order for it to support the claim. So the alternate hypothesis can either be a one-tailed test or a two-tailed test depending on what's being tested. So in a two-tailed test, it's one where the null hypothesis can be rejected by the sample being either too high or too low. And that would be captured by an alternate hypothesis statement that says not equal to some null value. So if the sample is significantly larger than the null value or significantly lower than the null value, we would reject the null hypothesis in either case. A one-tailed hypothesis is one where the null hypothesis will only be rejected by the sample being on one side of the sampling distribution, either much greater than or much less than, but not both. So as we see here, the one-tailed alternative hypothesis statements are going to have an operator that's either greater than or less than. Whereas in the case of a two-tailed hypothesis test, the alternative statement will have a not equals to as the operator in that case. And here's an example of a pair of symbol form hypothesis statements that go along with a one-tailed hypothesis test. We may say that as a null hypothesis that the population mean is greater than or equal to mu sub 0, some null value, and the alternate would be that no mu is less than mu sub 0. This would be an example of a one-tailed test. If we find a sample and test the sample and determine that it is has a sample mean that's below mu sub 0, then it possibly could support our claim. It would have to be significantly below mu sub 0 in order for us to reject the null hypothesis. But if the sample mean ends up being larger than mu sub 0, then there's no way it can support the claim. So this would be a one-tailed hypothesis test. And I contrast that here with a two-tailed hypothesis test, where the null hypothesis statement is that population mean is equal to mu sub 0, and my alternate statement is that population mean is not equal to mu sub 0. In this case, if I take a sample, well, if that sample mean is very low compared to mu sub 0, it could support our claim and cause us to reject the null hypothesis. If the sample mean is significantly higher than mu sub 0, it could also support our claim and cause us to reject the null hypothesis. So this would be an example of a two-tailed hypothesis test.